So, very happy to have Jim Crutchfield here. Thanks, Jim, for coming. And looking forward to learning your thoughts on hierarchy. I was thinking maybe we just have the next slide as like you at the top and everyone else below, but maybe you mean something else.
I tried really hard not to prepare. Habits die hard. So, thanks for this fantastic meeting. Setting some precedents, I hope. It's just absolutely wonderful environment. My kind of favorite. This fall has been great for me, giving talks, because for the first 6 months I can recall, I actually been giving talks barefoot. So there was this meeting in called Iliad in Berkeley, and it's this nice, crazy environment. Also, this is going to be less crazy. This is more stylish. So so I grew up barefoot on the beach. So why do we give these talks? Well, certainly there's technical information to transmit, to communicate, but a lot of times I think it's just learning how people think. So I thought I'd say a little bit, in fact maybe the whole talk is kind of like you have to put up with me talking about how I think. The issue of discovery and structure has been a key thing in my whole career, going back 45 years. It started out in kind of condensed matter, sort of complex materials and complex transport, and a lot of fluid turbulence. A complicated infinite dimensional system that spontaneously generates all sorts of structures, and we didn't, back in the mid-70s, have an effing clue as to how to describe that. And the problem is still remarkably open. In the 60s, Werner Heisenberg published this article in Physics Today about, kind of curiously at first, how turbulence was the biggest problem in theoretical physics. Of course, down to the modern physics, you know that particle physics is the most important thing that's ever been created. Odd, to have that message coming from the founder of quantum mechanics. Why? Partly because back when he was a graduate student, there was not a thing called a theoretical physicist. Physics was experimental. And although he was kind of this mathematical prodigy, for him to get a PhD at his university, the local faculty wanted him to be experimental. So the compromise was that he studied turbulence and carried that problem through his whole career, I think. The article in Physics Today, he's like, God, quantum mechanics is so linear, but look at turbulence. There's got to be other things we can do. I took heart in this. So we were really curious, and there were various proposals, some kind of more conventional to describe complicated fluid motions and turbulence. Certainly a huge amount of experimental work done, like aerodynamics, just tons of stuff, flame design, all sorts of technologically really important, and a lot of statistical and macro scale theories about momentum transport and that sort of thing that you could measure in the lab. But there was also a lot of really beautiful experiments on these just bizarre patterns that differently stressed fluids produced. And how do you describe those? Well, no, you just take photographs and publish them. We don't know. Until it was kind of the mid-70s, I would say, that finally the mathematics of dynamical systems started to become well articulated. And kind of mostly this development occurred in Europe, typically more advanced. Certainly the physics in Europe tends to be more advanced mathematically than the States. So it was Florence Hawkins and David Well who, very formal mathematicians, at least from a physics point of view, proposed that the fluid turbulence was described by these strict things. In fact, they just call them strange attractors, not having any better vocabulary. That there were the evolution of the governing equations, the Navier-Stokes partial differential equations, were described by some unknown but low-dimensional structures in the effective microscopic state space. And the idea was that this newfangled nonlinear dynamics, in particular chaos, which had been sort of articulated in the very, informal is not fair, it was quite jejune, by Ed Lorenz, a meteorologist at MIT, slowly kind of catching on. But the history of this, there's this kind of mathematical development, these abstractions a lot of it coming from the Russian school, Kolmogorov, people didn't really have a very, I'll use the word visual probably a bunch of times, a visual or graphical or notion of what these strange attractors were. They just were kind of there. You have this infinite dimensional system. You show that the density of energy dissipation is finite everywhere. Therefore, there has to be some lower than infinite dimensional thinking, asymptotically, that this set of states of the system is varying. But how that kind of statement translated into, oh, I see wavy vortices in co-wet flow, and pipe flow, sudden bursts, the translation between those things hadn't been made. So we all kind of got interested. I say we, there's some interesting folks. It was a very small field back in the 70s. Got interested in how you translated between theory, proposals like strange attractors, fractals, and all that kind of stuff that came up later. Translating that into theory. So we came up with this idea, partly driven by experiment. Oddly enough, at the time, several other graduate students and myself hopped in 1959 Ford station wagon and drove up to University of Oregon in Eugene to work with a fluid experimentalist up there. He had been studying co-wet flow, which is a fluid flow canonical. There are like 6 different kind of standard fluid configurations that are interesting. So you have a cylinder full of fluid, and then you put an inner cylinder rotating. And so what the system does, to say just really quickly, is that the kind of viscosity between the inner cylinder that's rotating and the fluid ends up transmitting angular momentum into the fluid, and then that gets transported out to the stationary outer cylinder. What you get, though, are these vortices, so-called Taylor vortices. And this is well understood. And people have been studying vortices in turbulent fluids for a long time because that's the dominant contribution to drag, say for airfoils and things like that, transporting energy away from other flying structures. So we're up there with Russ, and here we have an infinite dimensional system sitting on the experimental bench, and it's this fluid. But the nice thing, of course, is that there are knobs you can change, and as you change the knobs, initially low rotation speeds, all the fluid motion is laminar. We're actually visualizing this, interestingly enough, with fish scales. It's called kaleidoscope. You grind up, there's this guy back in Maine, in the garage, grinding up fish scales to a fine uniform size, so you get these horizontal flakes that are very tiny, and when you put them into fluid and stir the fluid, they orient in the direction of the flow, and then you can reflect light off of them and get some visual impression of what the flow shapes were. So that's what we were doing. Yeah, you're totally cool. You'll see. I'll probably get distracted and mention a whole bunch of things like that. But that's a little bit what that motivates what I do and how I think. It's very, very concrete, constructive. But how do you go between abstractions and physical behavior, structures, patterns, that kind of thing? It infuses everything I do. So, yeah. So it's all been about pattern discovery, and the kind of main idea we came up with was that you could, and this is even kind of a practical limitation, so yay, practical limitations. We didn't have experimental apparatus to measure the position, orientation of all these little fish flakes. You can see it, you can take pictures, and they're kind of beautiful and kind of cool. Wavy vortices, pairs of vortices splitting off, making other vortices, and all sorts of great stuff, and kind of cataloging all that. But how do you get to a state space? How do you verify or not, or disprove these various hypotheses? At the time, there was the Russian school who proposed that fluid turbulence, these complicated motions, were actually just a sum of simple harmonic oscillators tuned to different frequencies, called quasi-periodic behavior, with incommensurate frequency oscillators. And that's what generated the complicated patterns you saw. The dynamical systems approach was, there's these strange attractors, these small dimensional sets that are complicated, had very interesting structure in the state space, and had various instability properties that were being predicted at the time. So, okay, concept, experiment, connect. Well, we didn't have Avogadro's number of little Maxwell's demons looking at the fish flakes. What do? Well, at the time, we just had a laser. You just bounce a laser off some volume, focus the laser on some volume, and you see this kind of fluctuating stuff as the little fish flakes go by. Basically, you have some estimate of local velocity point. So, scalar time series. v sub x only at a point as a function of time. But you could see as you were playing with the knobs, yeah, okay, laminar flow. The angular momentum is just being transported linearly. The fluid is just all kind of moving together, but in a laminar way, and constant time series coming out from that point you're focusing on. Increase the velocity a little bit, then all of a sudden you start to see these Taylor vortices. So an individual particle, fluid, is kind of moving around this inner cylinder like this in a loop. And then it would kind of close back on itself, and then you increase the velocity a little more, you're adding more energy, you're stressing, there's more momentum transport from the inner cylinder out, and then all of a sudden the vortices start to wave. And then keep doing that, then they kind of wave, and there's a wave on the wave. Oh, Landau, theory of turbulence, quasi-periodic multiple oscillations. Turn a little more, then suddenly nothing was repeating. We didn't add a third frequency. There was just this complicated time series coming out, and you kept looking at it, and it wasn't like, oh, superposed sine waves like the previous kinds of behavior. It's just, I don't know, something. So that was the situation when we first got to University of Oregon and played with Russ Donnelly's Crutchfield apparatus. But then it's like, oh, come on. The time series has to have the information about what set of states it's visiting. So that was the origin of this notion. The first idea was to take time derivatives of this velocity as a function of time, and then also to do delays. Back then, it was really hard to do delays because taking an electronic signal and delay it required a fancy thing called a delay line, and those are very expensive. So what we did is we had also brought up, oddly enough, our little favorite dynamical systems microscope called an analog computer. And we had been simulating things like the Lorentz equations and other Whistler nonlinear equations. And we're kind of getting familiar with visualizing the solution of nonlinear differential equations on oscilloscope screens. In fact, we found Tektronix made these great large screen oscilloscopes. You plot X versus Y versus W, and even took two of them and made a little rotator, so you could take this three-dimensional object and kind of rotate it and project it on two-dimensional screens and cross your eyes. And there's all these beautiful structures there. The Lorentz attractors had two holes and looked like this rubber sheet. And so that's because of that kind of hand visual interactive exploration. When we went up to talk to Russ Donnelly and look at his co-ed flow, we were already kind of oriented towards thinking about these things, call them visual structures. That already there's kind of visual hypothesis that what's behind fluid turbulence are these relatively low dimensional but complicated manifolds, topologically complicated. And so that's how we ended up kind of coming to this idea of reconstructing from a single time series the geometry of these attractors, the kind of the hidden structures in the state space. You can't see them because you're always projecting down from infinite dimensions, but there can be these sort of shadows of these underlying recurrent structures, these fractal sets and whatnot. So that's, it says a lot how I think about things. Always looking for, it's a question of discovery. But discovery what? I mean, you could say, oh, I want to do prediction, but this was a shift because we wanted to discover so the geometric objects in state space, and it's a different thing than prediction. It's more structure oriented. Prediction is kind of like, oh, I have time series, there's some history, I want to get the next value. Maybe relevant to some discussion later on, but yeah.
It reminds me a bit of this Platonic hypothesis thing, at least with nonlinear dynamical systems. It like wants to express itself, and if you have any window into the thing, it has somehow embedded itself in that, and you have access to kind of the truth out there.
Yeah. I held my tongue the other day. No, absolutely.
Yeah, but it was also informed
a
bit.
Yeah, absolutely. Yeah.
Mm-hmm.
Yeah, I think the notion of, I mean, I said some slightly critical things just being facetious about Platonic thing out there, asking critical questions. But in fact, in a sense, this more dynamical systems view of structures in the state space, in my view, just to say it really quickly, is that Platonic truth. There is a way to get to some effective state space, know whether it's good or not, and test it, and then once you have that, there are different kinds of analysis, geometric, information theoretic, and so on. So so it's all about discovery of structure. That's my thing. So what I wanted to do today, in my failed effort to not prepare, I actually just want to give some examples, visual examples of hierarchy. So, okay, let me back up. Going to the Mojave Desert to talk about physics of intelligence, I try to think of what do I want to talk about? Well, I also information theory things, whatnot, but I thought maybe giving a bit of a hint. When I think about intelligence, what questions come up for me? And that little bit kind of entailed, how do I think about these things? And that's the history I just told you. So I'm going to give you some examples of what I think hierarchy is, but in the same kind of constructive visual way, and it'll connect up the things we've been talking about, but just, I guess my hope, and this could completely fail, it's a guess, that by giving some examples of differently structured processes, or dynamical systems that produce structured processes, partly kind of hinting at, we don't have all day, that the development of hierarchy is really very, very typical. We don't discuss it anywhere near enough, and it pervades almost all of the problems that we deal with when we're certainly working with experimental real-world systems. They're very complicated, they're very hierarchical. How can you even talk about hierarchy unless you know sort of what one level of the hierarchy is, or what a level of structure is, or level of predictability, and so on. So I'm going to kind of bounce around this and just give you some examples. I guess my goal is, if I could, which I think I'm going to fail, give you just some intuitions how to think about this. And these examples are familiar to some of you, or maybe all of you. But again, I want to kind of talk through them. So if you leave with some intuitions about what hierarchical structure is, I'd be perfectly happy. So that's kind of the goal. Not a lot of math. You know, we could go rummage around Hilbert's face, but don't want to do that. So yeah, so this is kind of maybe a visual or intuitive introduction to hierarchy, but then that means I tell you what I think about structure. When I'm looking at these systems, how do I look at them, and how am I trying to project my own notion of what structure is onto them to try to pull that out. So examples of dynamical systems that generate hierarchy, and what I mean is multiple levels of structure simultaneously. And maybe the hardest idea here, or maybe it's easier. I mean, looking at a system, the way I look at it is that there are multiple levels of simultaneous information processing, always. Now, I think that's kind of relevant to intelligence, because look at us. You know, we kind of walk through the world and we're kind of used to, oh, Alex, an object. Sorry.
You know, historically,
Yeah, Jim, when I first started working with you,
we've changed our view on how that is.
yeah, or, you know, vessel, that sort of thing. You're kind of constantly parsing. But I don't know, it's almost kind of, to me, when I have the right mental fortitude, it's a fun exercise to just slowly walk through your day and try to understand each component of your perception and how many different levels of cognition and interpretation and semantics do you need to hold to make that percept coherent to you. And I mean, you know, highest level, Alex, telescope, retinas, and so on, all the way down. And you realize it's almost uncountable, probably really is uncountable. At least if you want to do some modeling, hundreds of little nested structure. That's the way I see the world. It's just that complicated. Of course, what do? Is we talk about one level. Or we'll talk about machine learning. We go from a data set to a model. End of story. You don't talk about the model representing 16 different levels of information storage and processing. It kind of gives you a headache, but that's what I think it is. So we need some tools that let us at least start talking about these levels of structure. So I'm going to give some visual examples. It's supposed to be intuitive.
In that case, with machine learning, say you have some deep neural net,
Right.
Are you saying, well, we should be looking at the information processing through the layers, or are you saying more like we should be thinking of how it's interacting with society, at what level?
No layers. I'm really concrete. The social, psychological. I just kind of.
Okay.
This
So
was-
just like even just that thing.
This is really a mathematical talk
Mhm.
about geometry over time series reconstruction,
Mhm.
but applied to systems like transformers. You've got one level of structure coming out of the residual stream. Where else in the activities, even within these weird iterative function system Cantor sets, are there different levels of structure we can't see? That's just one projection, you know. So we should be thinking there are many, and I'm missing most, right? But we're really okay. So the main intuition is to think of the system we're looking at, the world, multiple levels of simultaneous information processing, and at different levels, and the levels are talking to each other. So I'm trying to maybe I'm playing a little bit off this idea of reconstructing from a scalar time series a three-dimensional strange attractor Well, what I'm saying, that's not really the whole object. What we reconstructed is something that can have many, many levels. And that's a challenge. You know, more data, more accuracy, longer time. You know, you're just going from the Taylor vortex wavy turbulent flow, that gives you the 2 quasi-periodic oscillations and 1 positively optimized x1. That's just kind of one model, one invariant set. I want looking at that set that we're reconstructing is actually representing multiple levels of information storage and processing. Now, is that helpful? Well, I hopeful. It maybe just complicates things, but I think that's the challenge. At least as I look at this, that's what we're trying to do. Hence why we appeal to various tools like information theory, because sometimes use that in some ways, it's limited in others, where there is at least kind of a calculus of generating a systematic hierarchy of different measures of information creation and storage, or at least it's posing these questions to you. These are metrics reasonably could go measure in an experiment. So, and hence we talk about anatomy of the bit and all these different information measures and so on, information diagrams and all that. Those are tools that help us articulate this exponentially growing library of different kinds of correlation dependence in the world. So, okay, but just examples. So this is a simple, I mean, some of you probably have done this, it's kind of wonderful. This goes back to the 1940s. It's going to evolve. I'm going to have to get it started.
I have to click.
Yeah. It goes really slow, but
Not doing something.
Yeah, it's going.
there you go.
Yeah.
I had to swap in the file. Anyway, this is a Petri dish, obviously looking down from above. In a Petri dish, it's 4 reagents. The recipes now vary. You can go online and look up the Belasav-Zhabatinsky reaction. Kids do this in high school now. And the interesting thing in the 40s was that this was inconsistent, according to the journal editors, with the second law of thermodynamics. You could not mix up chemicals and not have them go to equilibrium. What would equilibrium do? It's brown. It turns brown asymptotically. Just nothing. What do we see? Second publication that got rejected, it's just a transient. In that context, therefore unimportant. No. So this experiment led to all sorts of interesting kind of commentary and kind of new mathematics. Right about the same time, Alan Turing was coming up with his model of biologic morphogenesis. Very similar classical equation, kind of informed the analysis of this. You'll see on the slide, these are the various chemical reactions. I said there were 4 reagents. Okay, the difficult thing about chemistry is when you put 4 reagents into a Petri dish like this, you think, oh, there's some small number proportional to 4 reactions between, no. What they're going to show you is all these intermediate products get produced, and those are their own reaction. So this particular reaction has something like, people worked it up to 130 different individual reactions, and that's an approximation. So chemistry is hard. So this is kind of fun and simple, but it's a bitch to analyze it. But people still analyze this particular set of equations because where do we truncate? Which intermediate compounds are important, not important? So active area of study. And we are chemical soups. What I just said is true of us. So just think that I have these simple little 1-off, 2-off chemical reactions, and that's chemistry. That's wrong. Here, you have a really simple system that we design, and you can see these different reactions that spontaneously emerge. Interestingly, after a while, okay, so what you see here, if you were just looking at a point, the ion concentrations are oscillating. Well, what happens when you have a spatially extended system where locally some quantity is oscillating? Well, it's in space. What becomes important is the relative phase across space. What does that turn into? Those are traveling waves. Right? If I just looked at the stirred reaction, just mixed everything up, well, then I just see the concentrations going up and down. That'd be the homogeneous solution. But what happens when you do that in space, relative phase of the local oscillation becomes important, and those are the patterns we see. Now, why these particular patterns? That's what the folks are trying to analyze. So this is kind of, you get these centers of propagating waves, wave fronts propagating across the dish, and so on. Target waves, there's all sorts of very interesting. People have seen these reactions in, for example, to make some connection to other topics here, in the retina. some part of, what's her name, Schatz at Berkeley?
Carly Schatz?
Carly Schatz, yeah.
Yeah, and Marla Feller.
Marla, oh yeah, absolutely, yes.
Who
Yeah.
still lives there and
Yeah.
studies this. In fact,
Yeah.
anyway, there's interesting questions about training a neural net with that visual input.
There's also some kind of anecdotes from my reading literature relating these traveling waves in an active medium. Easy reaction is an example of active medium in epilepsy. How you have this tissue that's not only tasked by evolution to process information, make useful information deductions for the organism. It's active, it's processing, it's dynamical, and often you have instabilities like this. We're talking about epilepsy this morning, and there'll be these foci where the chemistry goes wrong in some sense, and it starts to generate these waves, and it trains other parts of the cortex. And what they see in the EEG study, especially, traveling waves across the cortex. And as this wave travels across the motor cortex, you convulse. So that's kind of a negative aspect of this. And active medium. There's this whole area of pattern formation theory. These are just a few examples. More structures.
This is also what happens in the heart, right?
Absolutely, yeah. Art Winfrey is a beautiful series of books on synchronization in heart, active medium, and also kind of categorization of different arrhythmias.
Yeah.
That was actually already appreciated in the 1920s by a radio engineer, Balthasar van der Pol. We have canonical equations, van der Pol equations for oscillation, but he actually built electronic analog computers out of vacuum tubes to study heart arrhythmias in 1927. He's got this great article, very short, like 2 pages, in Nature in 1927, where he's talking about a simplified version of 2 coupled vacuum tubes called triode oscillators. And he was driving it with sine wave. They did not have oscilloscopes back then, so he couldn't look at the waveform, but he was listening on the telephone receiver. And so he's got this great, very poetic kind of description of, I'm driving this, and suddenly these beautiful sounds like a bagpipe come out of me. What? And he's kind of drawing this kind of a picture of him changing the driving frequency of this sine wave and tone, but between these jumps between different tones, he kind of hashes it in. And he says, oh, we hear an irregular noise in the circuit, but that's not what we're interested in. Kill his fame. Because that was chaos. You can go back and build that circuit, and it's a chaotic attractor between these different, that's frequency lines.
Yeah, the subharmonic.
Subharmonic, yeah. Anyway, okay, so now you're supposed to think. The world is full of examples like I just showed you, right? And part of this is that they're readily, spontaneously forming patterns in organization. This obviously has something to do with how the system is dissipating, not only energy, but contracting state space and so on. But we'll put that aside. But there's a whole unequal thermodynamic story for these systems. So how are we going to think about this? Well, one thing is kind of metrics. So one thing we'd like to do is, was that BC reaction, the patterns it's producing, how random was it? Well, it seemed actually pretty ordered. But we have roughly 2 notions that we could think about kind of measuring. The system has maybe different degrees of randomness depending upon the control parameters, and there'll be some kind of deterministic complexity, by which I mean something like Kolmogorov-Chaikin complexity. You have some behavior, it's in your data, and you look for the smallest universal Turing machine program that reproduces that data. So that's the Kolmogorov-Chaikin complexity. You can also ask them, so the kind of information theory aspect of the Kolmogorov-Chaikin complexity is that its measure of the rate of growth of the Kolmogorov-Chaikin complexity is related to the Shannon entropy rate. So it is a measure of randomness, spontaneous production of information, but that's not the whole thing. If I just think of the class of processes that produced a given level of information, they're vastly different systems, different architecture, and differently structured, so we came up with another notion. So rather than using a deterministic machine, we use a stochastic machine where we discount the randomness. That's the statistical complexity. And here, this kind of interesting thing when you go from completely predictable to completely random, there's sort of this region where the system is most complex, most structured, stores more history. Kolmogorov-Chaikin complexity measures degree of randomness and not history dependence. Okay.
So here you're showing monotonicity, randomness, and complexity. I would actually expect it to even be more like linear rather than just monotonic.
It's artist's conception.
Yeah, you're
I'm not sure, we've done surveys where
Yeah.
where you can kind of vary these parameters and make plots just like that with your favorite information theory or statistical complexity measure. There's a whole zoo of different kinds of things. I actually think the claim would be how these different statistics scatter across this plane characterize a whole set of systems, and they're very, very different, but they're useful in kind of understanding what range an easing system. Well, through the easing system, there's going to be some kind of phase transition. So the effect of temperature goes up as you sort of increase, I don't know, the magnetic field or something like that. Here, there can be these phase transitions at different critical temperatures. Yeah.
I would say, like on the right, these are nearly independent measures, randomness and statistical complexity.
Actually, that's a key point, thank you, yes.
Yeah, like you can have
Yes.
either corner,
Yeah.
all four occupied.
Absolutely, right, so okay, stepping back a little bit, I think of, if you just plotted statistical complexity against deterministic complexity, it's kind of like an information theory-based phase diagram. They're like predictable crystalline structures, they're very random, randomized objects. Then in between, there can be these phase transition-like things. And it's just a huge zoo.
Mm-hmm.
So we use these complexity, when I say complexity, I mean memory, statistical complexity, entropy diagrams. We use that. It's just, first thing you do, you give me some weird Q-state POTS model. First thing I want to do, calculate those quantities. Density, information production, spatial system, and then density of memory. And sometimes these can be infinite too. So anyway, simple summary. I think when you first give me a system, there are two questions. Shannon said, how random is it? Information is the degree of surprise. That's a measure of randomness. Kolmogorov was interested in putting probability theory on firm computation theoretic foundings, so his whole theory is based on using determinate Turing machines. And then there's this other stuff that's capturing more structure. This discounts for randomness. So when you think about this, so Kolmogorov and Chaitin start off choosing a universal Turing machine as the descriptional language for your data set. Great. And you can show, as the Russians did, Brodnov did really early on, kind of underappreciated, that the rate of growth of this descriptional complexity, Kolmogorov-Chaitin complexity, is a function of the length of the data you're trying to describe. That is the Shannon entropy rate of the source. So in my mind, I simplify things. I didn't even talk about Chaitin Kolmogorov complexity more. It's just Shannon entropy. Deterministic complexity is basically disproportionate to the amount of randomness, but then there's this other quantity, this statistical complexity. To make the connection to what you do, if you want to kind of respect the setting of Kolmogorov-Chaitin complexity, you go from a universal Turing machine that tapes a finite state control, you just add in a random number generator. What that means is that now when you're describing your string, your data, you don't have to pay computationally for randomness. You discount that. Kolmogorov-Chaitin complexity is dominated by, in a sense, pseudo-random number generation for the apparent stochasticity. So the deterministic description has to describe the randomness. When you move to this conceptual framework, just put your finger in the heat bath. That's zero cost kind of thing. So, and then what happens is you discount for that. What pops up are these measures of structure and symmetry and memory. Okay, so how do we get there constructively? Kolmogorov-Chaitin theory and algorithmic information theory, length of the Schroeder's universal Turing machine, beautiful mathematics and totally practically useless. People do try to do it. So this is a question back in 1980. How do we go from measures of randomness, because I'm studying chaos, to measures of the other thing that I'm seeing? Well, that's where the causal states came up. That was the answer. And this is partly based on the intuition that when you're looking at the time series to reconstruct these attractors, what you're doing is you're looking at the past and trying to predict the next state in your effective state space. We call these morphs, but it goes all the way back to geometry from time series. There are pictures in the original physical review letter of conditional distributions in morphs.
Which letter?
It's the geometry from a time series, paper in PRL, 1980. Yeah, so we are thinking about moving from exact deterministic descriptions to probabilistic, and the first thing you do is you look at your reconstructed data in the state space, and you do conditional distribution by doing cuts in space. Okay, so I won't belabor this because it's familiar. Okay, so now here's making the connection to thinking about hierarchy. That's not the end of the story. That's just the beginning of the story. So what I want you to think about is we go from the data, we look at histories, and then do our best with the given available stored information to predict the future. If the process is any kind of stochastic, there'll be a little residual unpredictability. There'll be alternative futures given that particular past. Move to another time, well, maybe there are different alternative futures because now you have more information, but that can happen again. So the idea here is that you have these conditional distributions, the sort of predictive complexity of the process is really the number of distinct predictive conditional distributions you have. Okay. You write down to the equivalence relations, which physicists don't like equivalence relations. This has been such a bear over the years. Anyway, we're talking about the data here, but this is just the beginning of the story. The way I want you to think about hierarchy is I can start down here, level 0, whatever. I have data. So my measuring instrument is going from measurement state to measurement state to measurement state, and I'm seeing different, say, locations in the state space where the system is. It's just a time series, okay? So a series of measurements. Then what I was just saying, we want to look at these predictive conditional distributions. I can think of those in a kind of data structure that looks like a tree. If I see a 1, 1, and then down here I can see a 0, 1, that's one of these morphs, or these future conditional distributions. But it can be that these various distinct future conditional distributions, these morphs, actually repeat in structure somewhere down in the tree. Oh, so we're done. Let's factor that out. That takes you to the notion of automaton state. Well, sometimes when you try to do this even, you end up with not this infinite tree, but now I have a set of states. The number of these conditional distributions can be infinite, as Alex showed. So, why stop? Right? You just look at this now infinite state machine and look for conditional distributions of those, and then group those, just like you did going from here to here, just like you did going from here to here. Well, sometimes those machines are infinite in different ways. Keep going. So the idea is you keep moving up this reconstruction hierarchy until finally you get some kind of finite representation. Well, you can also kind of define processes where that never happens.
Yeah,
It's an infinite hierarchy. Okay, so this is very much motivated by or inspired by, in the theory of discrete computation, Chomsky's hierarchy. So the computer science folks back in the 40s and 50s and 60s, Noam Chomsky being kind of the main proponent in the 50s, came up with, he was interested in human language, and sort of came up with kind of like 4 levels. At this point, with using this predictive equivalence, I don't know, maybe you can just keep going. So to me, it's kind of a natural hierarchy. At every stage, you're trying to find some effective predictive states, but they're kind of built on top of other states. So maybe I go from here to here, and I call these causal states, but then I get groups of those, so meta-causal states, meta-meta-causal states, and so on. Okay, so that, just to say it, is when I say hierarchy, this is what I'm thinking of. And also, there is the process, there's a reality down here, and I can look at that in different ways. Maybe at some point it's a finite description, great, I can work with that calculationally, but in a sense, they're all operating at the same time. These are different levels of information processing. So you can look at any given process and try to represent these different ways, and those things are all going on. And different kinds of information being created and stored. Yeah.
Sorry, I'm not understanding how to go from the finite automata to the string production. What's the A back arrow?
Yeah, I'll give you some examples. Yeah.
Okay.
Yeah.
For the specific string production machine, can you say like how to interpret that thing?
Okay, well, I made little squares here to mean they're sort of different from these circles. I put a string in here, and then based on the structure of this, it tells you how to take that string and replicate and mutate it. I'll give you an example. Morse 2, it's already been mentioned. Morse 2 is an example of this. Yeah, this is. I wanted to make sure I got here so you knew kind of the bigger goal in mind. And now let's just do some examples. So all examples, and some of these will appeal to some of you and some not. Okay. So going from finite to infinite memory. This is the workhorse in the area here. This is this quadratic function on the unit interval, has a control parameter, goes from 0 to 4, and I can look at the long time asymptotic states as I increase the nonlinearity R. It's just a parabola, and we had this famous bifurcation diagram. There's a limit cycle, period 2 limit cycle, period 4, it all accumulates at a particular value, around R equal 3.7, and then from that point on we have aperiodic behavior, except occasionally we have these windows of periodicity that do period doubling all over again. So in fact, you see this sort of scatter of states up here, they're hopping around randomly. In fact, the logistic map was used by von Neumann as a random number generator for the Manhattan Project. Unfortunately, there's just like one little abstract in the bulletin of the AMS that describes this in 1945. I think it got declassified.
R equals 4.
Yeah, and they had a bunch of other ones too. There's this great survey paper in the Polish Academy of Sciences proceedings by Stan Ulam, who's also at Los Alamos at the time, where they were just simulating all these different maps just to see what could go on. And he's got these oscilloscope pictures. It's fantastic. Period doubling, quasi-periodicity, all the stuff that we, 30 years later, we're studying. Ulam taking pictures of this stuff on the new digital computers. Yeah, so things get more complicated. Period doubles, 1 to 2 to 4 to 8. Diverges here. Questions, so what does that look like in terms of these? I said, I have a new system. Two things I want to calculate is degree of randomness, amount of memory. So here you go. This is just an experiment, different R values, different degrees of randomness across the bifurcation diagram, and different amounts of memory. And what you see, the solids left, the things we can do analytically, is kind of a phase transition. Everything down here is periodic, no information creation. Everything up here is some degree of random. And then right at that onset of chaos, you have infinite period and infinite memory. So you can now actually calculate the number of these causal states as a function of the window length you're looking at. You want to describe all the statistics with the length 32, length 64. I keep trying to do this automata modeling stuff, these predictive states, and they keep growing. And this stuff you can all do analytically, by the way.
That's at the onset of chaos?
Yeah, right at the onset. And interestingly enough, sort of the most memory complex process is right at the onset of chaos, where there's zero entropy rate. It's actually kind of an interesting lesson there. Sometimes stochasticity can ruin some of these long-range correlations. Yeah, so what's going on now? I started with arbitrarily long string, and now I'm saying, oh, my set of predictive states, that's arbitrarily large, it's growing, in fact that curve never converges. Where's the structure? How do I apply this idea of predictive equivalence relation again? Well, you can write out these machines. This is an approximation of sort of the first level causal states, like I'm having them loop back into a start state here. But if you actually squint your eyes, what you see are these long chains of complete predicted zeros and ones. So take those out. What you end up with are these states that are branching, and then what you see is that there's actually kind of a string operation on these deterministic sequences. And that is what's called the Morse-Tui sequence that was discovered in the 1920s by Morse and Tui, who were interested in trying to explore the range of stochastic processes. How complicated could they be? You can show the Morse-Tui sequence, and it's a simple grammatical production. 0 gets replaced by 1, 1. 1 is followed by 1. So there's a simple way. You can just kind of, the next step of the reconstruction, you look at kind of replacement schemes for going to longer and longer words. Every one of these branching transitions doubles the length of string. But basically what you do is you take this, you invert the last bit and then copy it to itself. So that's just a little simple replacement grammatical operation.
I just want to make sure I'm understanding.
Yeah.
The thing on the left I can interpret as a HMM.
Yes.
And the thing on the right is a different type of thing.
Yes,
Yeah.
right. So in fact what's happening, well even this, to say HMM, it would be, kind of by implication, you keep doing this, it would be infinite state HMM.
Yeah.
But again, I don't want to work with infinite representations, that's not helpful.
Yeah.
But I do see there's a lot of regularity in the branching structure, therefore I can invent kind of metacausal states, and that's actually what these branching states are, that group together pieces of this machine. So that's moving up that hierarchy I just showed. But it's the same equivalence relation, predictive equivalence relation. You have,
Well, yeah. So I'm trying to figure out the statement, it's the same equivalence relation.
I'm looking at time series of these causal states. So I'm looking at
But you still.
time series
Yeah,
of
yeah.
this kind of level 1 causal states, and then I look to the future, and there'll be some various options of branching into the future.
That sounds
and
like
I just group those together.
taking the causal states themselves as the data.
Yes, exactly.
Yeah.
Yes, yes.
Right.
Right. You just do it again. You have this infinite state, explicit state, level 0 state, and then there's this regularity that you
Is
can
there
pull
not
up.
one more piece of structure, like one more thing, which is like you don't get another HMM now, right? You get a different type of structure.
Yes. So I apply the equivalence relation to the previous thing,
Mhm.
right? And then I imagine, kind of innovate, if you will, that there are 2 registers that hold strings.
Ah, yeah.
And then I kind of infer that there are these string production rules that manipulate those. And these are, in a sense, the strings that were on the transitions in the previous diagram. Right. So yes, there's a little extra,
Yeah.
little extra magic here. Another step you need to do. But then when you do that, well, especially if you make connection to historical literature, this structure with these particular string production rules is something called an index context-free grammar. In the literature studied by people in computer science because they were interested in parsing computer languages. This was later used in the 80s, actually by Chomsky and friends, as an approximation of human language. Pretty good one, apparently that level of. And it's called the index context-free grammar, sort of like a context-free grammar with these reproductions, except that it's indexed at any moment in time. You're sort of putting symbols on this stack, but then you can say, oh, I need another stack. And you operate on that substructure, and then you're done. You pop it off, go back to the previous step. And the literature in the 50s and 60s, these different kinds of computational models, it's vast. Like I said, was saying kind of earlier, this is based on choosing stacks. Put a symbol on, pop, pop, okay? You can also do the same, so there's a whole construction for machines that use counters. FIFOs, first in, first out, da, da, da. And they generate their own hierarchies, and these people study this stuff, 50s and 60s. It all kind of died out in the 70s. If you go talk to, computational complexity now, this is old stuff.
Reminds me a bit of Ashwin's talk on refactoring the search
Oh,
space.
absolutely.
Like, well, if I gave myself a stack.
Yeah, absolutely.
Yeah.
Now, there's a lot, I think, interesting parallels. And part of what I'm saying is it's really interesting to go back and read some of this earlier literature in, formal language theory. They're really interesting. Why these different structures? I mean, to a certain extent, when you get up to these effectively infinite state models, it kind of gets it's horizontal, and it becomes more important. What computational model you choose? Counters or push-down automata? That's still to be explored. That's why we're kind of acting. I was asking earlier about, we were thinking about this residual stream. How do we know where it is? Is it naturally map this into something else? Yeah, so that's kind of where this is coming from. So, yeah.
So with these, infinite state fractal processes that you're looking at,
Right.
have you been considering, what additional, say, stack or computational device might turn it into a more finite representation?
Well, this is okay. Yeah. So this is already to use that. Yeah. This is already that finite representation. This re-representation of it is just me making connections to the computer science literature, so they would listen to this. This is already this model that we inferred was already fine.
Okay. I guess I was asking specifically about like the fractal.
Okay. But that's another branch.
Okay.
So we're not talking about probabilities at this point. This is mostly topological.
Oh, this is all strictly.
Because, why can I do that? Because of the onset of chaos. It's the onset of chaos, which means the entropy rate is 0. There's not really an effective notion of stochasticity that's kind of inherent. Right? There's no kind of chaos we're picking up. That was further up in the bifurcation diagram. But let's do the next example. Okay, so I'm trying to give you these different examples, emphasizing this notion of hierarchy, simultaneous levels of information processing. So, space is memory. Well, okay, probably you all know about these cellular automata. I have, say, a one-dimensional spatial lattice, local states of zeros and ones, and this evolves over time by looking up neighborhoods in some lookup table and then replacing. So these are the elementary CA. And here's an example Rule 18, I start at time 0, random bit, and at each step, in every neighborhood, around every site, looking at its neighbors, I apply a lookup table, this one in particular. If I see 001, 001, or 100, I replace the center site the next time with a 1. Everything else goes to 0. And this is the space-time diagram you get. Looks kind of random, looks kind of ordered. There's these large triangles here. Actually, it's interesting, your eye focus on those things. Those are not the most important thing about this space-time evolution of Rule 18. It actually turns out, maybe you can see this, I'll show you shortly. There actually is an interesting hidden structure here. That is what you need to know to write down the correct joint distribution over space-time patches. Pairs of ones, pairs of blacks. So notice up here, adjacent ones, and they propagate down, and then when this one comes into the top of a white triangle, there's another one comes in, they pairwise annihilate. So there's actually structure you can discover here by doing predictive equivalence. What does that look like? So here's just a larger space-time diagram to make the effect more dramatic. So like 200 lattice over 200 time steps, looks kind of noisy. Although it's deterministic, it looks noisy. And then once you realize and discover the hidden structure by doing space-time versions of these predictive equivalence relations, you find these particles. So this is just running a little local spatial filter over here, basically looking for pairs of adjacent ones. And what you see is that there are these large areas of space-time that are completely predicted. They're described by the language 0 wildcard. And then that kind of gives it a kind of a spatial period two-ness. Like the wildcard's always in one location, and then that breaks down whenever I see a pair of one, it breaks that spatial period two-ness. And that's we call these domains, the regular thing that goes 0 wildcard, and they're domain walls, borrowing from Nets Matter kind of notion. And these things propagate around like localized perturbations until they get close to each other and they pairwise annihilate. So here's another notion of hierarchy.
I'll point out we're at 52 minutes. If you want to take another, maybe 5 to 10.
Yeah, that's good. So at this level, the finite representation is not applying this local lookup table over a length of 200 lattice. That's kind of big. That would be the raw data. I can actually write down a little stochastic grammar where there's a particle called alpha that each time step it moves left or right with fair probabilities, and it gets close to a neighbor, it pairwise annihilates. I told you enough, just with that description, finite description, to predict all the statistics that you're looking at for those.
But even all the stuff that happens within the domain, it looks like there's a lot. Looks like there's a lot of interesting stuff happening.
Predicting the
within
statistics. Yes, I can predict the statistics, not the unique particular.
I see.
Yeah.
This
Then there's a shift. That's important because I captured some of the regularity, but that's running on top. But when I do that, I kind of give up the determinism of predicting where the wildcards are and what their values are to this stochastic particle reaction. Alpha plus alpha goes to naught. Right? So there's this trade-off. I got rid of some deterministic structure, but this is saying that's kind of irrelevant. All I need to know is that it's 0 wildcard with fair probability for those large patches, and then just that these domain walls diffuse around the pairwise annihilate. Just that short visual description gives you complete prediction of all the statistics of the space-time patches. Yeah.
I'm just wondering if you had made some decision about what you wanted to keep and not, or whether it really is just strictly a matter of what's deterministic and what's not.
Okay. We're discovering what that is. I'm saying filtering here. There's a way of constructing using the predictive equivalence relation, constructing exactly what these filters are. And you can show in a mathematical setting, that's exactly the right description, capturing that stuff.
But it's like the white stuff, it's not like you replace that with IID, because it's still like triangles
Yeah,
that way,
yeah,
not that
yeah.
way. But it's like a domain.
This random stuff here corresponds to being over here. Yes, exactly right. Yeah.
Mhm.
Yeah. Yeah. Okay, so let's just finish up here. Just another example, but I can do this one visually. This Rule 54. It's kind of interesting because it has 4 particles, but discovered exactly the same automated way. They're kind of heavy particles here, and then these little light gamma particles, we call them, they kind of knock it around. It's sort of like a deterministic version of Brownian motion. Okay. Again, this is lattice of bits and only nearest neighbor rules. I find those 4 particles, and so I kind of pick up regularity. I can write down little particle interaction rules like a chemistry, effective chemistry. And again, that describes all of the statistics you're seeing. Not the particular evolution from that particular initial condition, but the structures. That's the point. And again, simultaneous information. Here's the raw data, but hidden in there is all of this stuff going on. And these particles are sort of the loci of information storage.
Sorry, these are the same rule? No.
Yes, exactly the same rule. All I've done is filter this.
Okay.
The background here, you can see it's a little bit kind of, it's actually periodic in space-time.
Yeah, that domain looks the same everywhere within.
Yeah, and you're factoring that out.
Yeah, that's easier.
Within here, the space-time conditional distributions are all the same. Therefore, that's going to be kind of like one node in my now higher-level state machine. Again, and you're discovering this stuff. It's not like I need to do, invent that they're just 4 particles. Yeah, they're 2 heavy particles and 2 light particles. Okay, so we can finish up here. I was going to talk about another kind of system where we're evolving these cellular automata using a genetic algorithm so that the cellular automata do interesting information processing called density classification. But I'm going to skip over that. But you can also discover these emergent particles in the evolved cellular automata, these spatial processors now. Okay, so here's a good summary. This is what I've been talking about. It's this cartoon picture. There's some sort of regularity in the space of systems that's revealed by looking at the memory and the degree of randomness. Roughly analogous to kind of like a phase transition where you see the most interesting stuff. But then if that representation is infinite, you do it again. The equivalence class again, and keep going. So basically this hierarchy in terms of predictable equivalence is actually, it goes all the way up. To where? It goes. I mean, depends on how masochistic you are, what kind of system you want to invent to study. They get harder and harder to describe the structures they produce. Natural trade-off. That's also true in the Chomsky hierarchy. It's harder to learn models in hierarchy, like by the time you get the universal Turing machines, it's undecidable. So, same kind of trade-off. Anyway, so here's a little task. I mean, if I was moderately successful at convincing you that many systems have multiple simultaneous levels of information storage and processing and are related to each other, you can kind of discover them at the different levels. What I'm really interested in now is not kind of the way I was talking before, going from data, huzzah, equivalence relation, getting a new level of causal states. I want a system that does that 2 or 3 times, 4 times. Infinite, if you could. I want to invent an example of a system, stochastic determinist, I don't care, that actually has 3 different identifiable levels of structure. And that, I think, is going to help us think about intelligence. That's kind of my punchline. It gets us ready to think about how many different layers of information processing are going on. It even makes if you could do that, how would you relate one level of information processing to the other? Whole interesting set of questions. I mean, I would say same sort of thing looking at the transformer stuff. There'll be other places, other kinds of models that pick out these different levels of structure, and then there's going to be a lot of interesting questions about how the information processing at these different levels, the different levels provide different semantics to the other levels.
Yeah.
So that's hopefully a roadmap for fun. All right. Just some evolution examples. Whitehead was really kind of great on this stuff. He's got this Process and Reality book, just chock full of anticipation of a lot of this work. It's fun to go back and read that. Let's see. Okay.
Sorry, can you just go back?
Oh, sure. This one? Oh, you're reading it? Oh, I could read it for us.
Sure.
Yeah? Okay, so order is not sufficient. What is required is something much more complex. It is order entering upon novelty so that the massiveness of order does not degenerate into mere repetition, and so that the novelty is always reflective of the background of the system. There's this wonderful tension there between these things. And that's how I think we think. It's not a static picture that I was giving you, raw data and structure. What we're doing most fundamentally, it's a dynamic balance between these things, constantly changing. Rewriting, changing. Okay, thank you, thank you, thank you.
Cheers.